Welcome to Brain Vision.
Hi everyone. So what we have is a vertical cylinder that's initially at room temperature, and right now the properties in the cylinder are we have air that's at a pressure of 300 kPa at a temperature of 20 degrees C and has a volume of 0.2 cubic meters. There's a valve and the air is allowed to escape at a constant pressure and temperature, so the volume actually goes down by half. So this volume is going to be equal to 0.1 cubic meters, and our pressures and temperatures are going to be the same. And now what we're asked to find is the amount of air that has left the cylinder, so the mass that is exited, and the amount of heat transfer that occurs during this process. So what we're going to do first is we're going to go ahead and find our gas constant. So since this is air, we look up the gas constant and we see that R is going to be equal to 0.287 kilojoules per kilogram Kelvin. And then what we can do is define our system. So what we're going to do is define the cylinder as our system, and that's going to be the control volume since the mass is going to be crossing the boundary of that control volume. So when we do our mass balance, we'll see that the mass coming in minus the mass leaving is equal to the change in mass of the system. Now, as given by the problem, there's no mass that's coming in. So all we have is this mass that's leaving, so that's negative ME, is equal to M2 minus M1. Now, if we just solve for ME is going to be equal to M1 minus M2. Next, what we're going to do is we're going to do our energy balance. So we know that the energy coming in minus the energy leaving is equal to the change in energy of the system. Now, there is work, and we're going to assume that there is heat transfer occurring as well, since there's nothing in the problem that tells us there isn't. So we're going to say Q in plus work, the boundary work, minus the mass that's leaving is equal to M2U2 minus M1U1. Now what we can do is use the ideal gas law to solve for the initial and final masses. So we can say that M1 is going to be equal to PV1 over RT, and we actually know all these quantities, and we find an initial mass of 0.714 kilograms. Similarly, for the final mass, PV2 over RT is going to be equal to 0.357 kg. Now this is just half of M1, so we see that M2 equals 1/2 of M1. Now from the mass balance, we know that ME is equal to M1 minus M2, so this gives us a mass that has left the cylinder as being equal to 0.357 kilograms. So that is one part of our final answer. Now as we look to solve for the heat transfer, we actually need to first recognize that this is a constant pressure process. Therefore, we can say that H is going to be equal to U plus P delta V. Now because of this, what we can actually do is combine the work and delta U terms into a delta H term in our energy balance. So recall that our energy balance looks as U, or Q, plus the work, minus MEHE equals M2 U2 minus M1 U1. Now let's just isolate Q. We see that Q is equal to M2 U2 minus M1 U1 minus W plus MEHE. So what we can do now is actually go ahead and combine the U and the W term to give us an expression for Q in terms of just the enthalpy, and this gives us MEHE plus M2H2 minus M1H1. So the equation condenses a little bit. Now let's recall that this process is actually isothermal because the temperature remains the same, so therefore the specific enthalpies are also staying the same. So HE equals H2 equals H1, and also recall that the mass that exits is equal to 1/2 of M1, which is equal to M2. So now we can actually go ahead and use these relations to simplify this equation here. And once we simplify that, we see that Q is simply equal to 1/2 M1 plus 1/2 M1 minus m1 all multiplied by h, and as you can see, this results in 0. So therefore, our actual total heat transfer in this process is 0.